Hi everyone, welcome to this week's online video lecture, your first online lecture, number one of two that you have to get through while I'm away. So this week we're going to look at oxygen consumption, deficit and debt. And we'll find out a fair bit about those by the end of this presentation, which should be about 20-25 minutes. Okay, you should be pretty well used to how oxygen is delivered and used in the body. So I've really just put this slide here for you to just have a look at it and pause the video now if you need to study up on that. Otherwise I'm going to move straight past it and not talk about this at all. This one we don't need to spend too long on either, the relationship between exercise intensity and oxygen consumption. This is a graph plotted with power output or exercise intensity on the x-axis and oxygen consumption on the y-axis, and it shows that as you increase the intensity of exercise, you're also going to consume more oxygen in the body. That's simply because your body wants oxygen so it can generate energy aerobically. Very simple, another strong linear relationship between those two variables. Okay, how do you measure oxygen consumption? It's exactly like this. You put a mask on, you breathe air as you normally would, and you collect the expired air using some sort of device like this. You can see this is different to the device that we use. In fact, this one has got a mouthpiece in, so it's even more invasive than the one we've got, and that's the one you'll be using in the lab on the Wednesday. So very quickly, just revisiting how we can measure oxygen in the body, how we measure oxygen consumption. It's really simple. We know that you've got 21% oxygen that you breathe in, or just under. Okay, so we know that we breathe that in. We know that when we breathe in oxygen that you're going to use that oxygen in the body to produce energy, and therefore the air that you breathe out, the expired air, is going to contain less oxygen, and we simply just collect that expired air, analyze it, and calculate the difference, the oxygen difference, that is the percentage of oxygen that has gone out. So here's a quick example. Let's say the difference is 5%. Yep, i.e. you breathe in 21%, you breathe out 16%, giving you a difference of 5%. And you need to know 5% of what? It's 5% of the total volume of air that you breathe in, okay, which also happens to be the amount of air that you breathe out. Let's say it's pretty normal when you're resting to breathe about 25 liters of air in a minute. Okay, so let's say you breathe, you take in 5% of the oxygen out of 25 liters of air, okay. And I'll give you a moment to do that mathematics and let me know, and come up with an answer. You can't let me know, but come up with an answer and I'll let you know if you're correct when I put the answer up in a minute. So do that now on your calculator. You should have your phone next to you. Just quickly calculate that. It's good to have practice calculating percentages. Tick, 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 tick. Okay. Put those numbers in your calculator. Boom, boom, boom. Done. Okay. Hopefully you went something like 5% times 25 or 0.05 times 25, and it gives you it gave you a value of 1.25 liters. What that would be telling you, well, you've consumed 1.125 liters of oxygen in a minute. Pretty normal. Okay, so now that we know and have just revisited how you measure how much oxygen you consume, we're going to soon just have a look at oxygen deficit. And before we do that, just do a quick revisit of the energy systems, how they work over time. It takes a while for the aerobic energy system, as you know, it takes a while for the system to get to close to its sort of maximum capacity. Okay, 5 minutes it might be at sort of 95% of its capacity. Because it takes time for the aerobic energy system to wind up, then it means that in the initial stages of exercise you have a shortfall. You have a shortfall of oxygen that has to be met in some way. The body tends to want to supply the amount of oxygen that's going to meet the demand of the exercise. So if you go and run at 10 kilometers per hour, the body's going to demand a certain amount of oxygen to fuel that intensity. Okay, but you can't meet it initially. So let's have a look at what happens. What happens is when you're at rest, your body is also demanding an amount of oxygen. Okay, and here it looks like it's about 0.2 liters. When you start exercising, if we follow this red line up, okay, this one, follow that up, you can see that oxygen uptake, it increases fairly quickly from the outset, but it takes a while to hit what we call steady rate or steady state. I'll also put that in there. It also takes a steady state. These are interchangeable words. Usually I use steady state. I find more people probably use steady state, but use whatever you want. Steady state VO2. It takes a while to reach steady state VO2. Steady state basically means that the amount of energy that your body is demanding, or the amount of oxygen your body's demanding, is now being met by the amount of oxygen that you're providing, i.e. the amount of oxygen that you're consuming. Okay, it's called a steady state. The area shaded in the purple here indicates, or it's just showing how much how big the shortfall is of oxygen. Yep, i.e. the bigger the shaded area, the bigger the shortfall of oxygen. If we were to say increase the intensity, that would increase the demand for oxygen. So I've just drawn that in a new line, and it's going to take longer to get there. What that gives us is just a larger shaded area, and it just means that we have to make up that shortfall in some way. How is that shortfall made up? It's met by the anaerobic energy systems. Okay, so yeah, if you're not getting the oxygen, you're going to have to find that energy somewhere else. Anaerobic, phosphagen, glycolytic systems. And you can see here that it takes about between 2 to 4 minutes to reach a steady state. That's pretty typical. You might find different values when you do the exercise in the lab. Just showing the same picture again, just to summarize. We have a deficit because oxygen uptake is slow at the beginning of exercise. It takes a while for the aerobic energy system to kick in, and the difference is provided by the anaerobic energy systems. You've probably also noticed that there's a blue line. Okay, there's a blue line here, and that blue line's just showing what happens in a trained person. Yep, that simply the oxygen uptake is faster, and the rate that oxygen is taken in, the rate of increase, so basically the steepness of this curve, is called oxygen uptake kinetics. So oxygen uptake kinetics sort of describes how quickly you reach a steady state. A trained person reaches a steady state faster. And there's the prompt right there. Okay, this is the same. Now, don't get too confused by this slide. I've thrown it in because what it does is it puts the energy systems in behind the image. It basically, if it's going to confuse you, just skip it. Which I do find it can be confusing. I was tossing up whether to put it in or not, but I've put it in. It shows that here's your oxygen. Just trace this line. It shows your oxygen uptake at the start of exercise, and that sort of slow increase that it goes through, and then it's got your deficit above it, which is the shaded area, but it's just put in the energy systems contributions. So you can see here the glycolytic system. Okay. is going to be really dominant in the first few minutes. If I put a sort of line at the 50% level, you can see from about, you know, less than half a minute up to sort of 2 minutes, okay, that system is going to be providing more than 50% of energy. So the glycolytic system is going to provide a lot of energy during that oxygen deficit. What does that mean? Well, it means that, as you know now, that if you're not getting enough oxygen into the body, okay, because of this lag, then, and the glycolytic system is working, then some of those hydrogen ions are going to convert to, are going to combine with pyruvate and can convert to lactic acid. So you're going to get some lactic acid buildup at the start of exercise, usually. And what do you do with that lactate? Well, you can use it during exercise. You can start to oxidize that lactate, or if the intensity is really high and the effort's really short, then that lactate might continue to build up even when you've hit a steady state VO2. Okay, and this these two graphs here basically show that when your oxygen deficit is high, it's measured in liters. The oxygen deficit is the amount of oxygen that you're short in liters. So if it's sort of if you've got 5 to 7 liters of oxygen that you're not providing the body, that the body wants, you can see here that the muscle lactate buildup in the body is going to be really high. And also, if you've got a big oxygen deficit, you're going to use a lot of phosphagen, so you're going to deplete those stores. So these two graphs, what they basically show you is the higher the oxygen deficit, the more glycolysis is occurring, and that's represented or reflected rather by how much lactate accumulates. And it also shows how much phosphagen you're going to deplete. Okay. Here's a question. Yeah, why do you think you're still puffing? Let's take the scenario and think about, you're running along, you hit a red light, you stop, you can't go across because you'll get run over, so you stop at the traffic lights and wait for the green light. And when you've stopped running, you're still puffing. And the question is, why does that occur? So I'll give you a little bit of time to just ponder that question. You can have a think about that. How long do you need? A minute? More? Okay, you can't respond, obviously, so I'm talking to myself here. The answer, or the conclusion that you've hopefully come to is, well, actually, before I get to that, you might be thinking, actually, it's a little bit harder to answer than you might think. That's not. Yeah, okay, why am I puffing? I stop exercise. Why is it that I'm still taking in more oxygen than I actually need? Because if you stop running, you should be able to just return immediately to a resting level. It's not like, well, do things take a while to wind down? Maybe they do, but there's some other reasons to explain why you're still puffing, and we'll have a look at that. It's called your oxygen debt, and it's like, if you go to the bank and get out a loan, then at some point you're going to pay it back. And think of it like this: your oxygen deficit is exactly that. It's like you've taken out a loan, because what's happened here is, in here, this space, you've used your anaerobic energy systems, okay, and they're not sustainable. The aerobic system's sustainable. It's a pay-as-you-go system. You supply oxygen, and then when that oxygen's there, you use it. The anaerobic systems will keep working regardless of whether it's a sustainable level of exercise or not. So here you sort of, during the oxygen deficit, you go into like an overdraft, or you've taken out a loan, and it's like an oxygen loan, I guess. And at some point you're going to have to pay it back. You pay it back, at the end of exercise. What are you paying back though? What's causing your oxygen consumption to remain elevated, and what's causing the debt, is that some of this lactate that's that's accumulated during the deficit now has to be paid back in this phase here. So you might have lactate levels higher than resting levels, and that will mean that oxygen consumption remains elevated to help clear that lactate. But the argument is, so this was the traditional theory behind the oxygen debt, that you need to consume more oxygen to remove lactate. But it's a bit of a flawed theory, because what really happens, as you know, if you go on a leisurely run, yeah, at the start you're going to use a bit of glycolysis and maybe accumulate a little lactate, but you can actually oxidize that lactate during exercise. You don't have to wait till you finish to remove that lactate. So there must be some other reasons that explain why you have an elevated oxygen consumption when you finish exercising. And some of those reasons are that a lot of them relate to your metabolism being stimulated. So when you exercise, your body heats up, and when your body heats up, that stimulates your metabolism. That causes you to require more energy. If you've got a higher metabolic rate, more energy being used, and therefore you need more oxygen. So that's why one reason your oxygen is going to remain elevated, because your metabolism is elevated because your body temperature rises. Hormones that are released during exercise also stimulate your metabolism. And there's several other things that are going on there. Your hemoglobin during exercise it carries the same amount of oxygen, but it can, or actually it can sometimes carry a little bit less. It usually carries the same, but it gets more taken out of it in the muscle, and you post exercise you take in more oxygen to replenish or reload your blood. Think about it like you reload your blood with more oxygen, because the levels are a little bit low. You've used a lot during exercise. I don't think we need to give you too many more reasons than that. The whole point is that you're trying to return your body to homeostasis. Yeah, it's that state that your body likes to be in, that where everything's normal. Lactate levels are normal, oxygen levels in the blood are normal, body temperature is normal. It's trying to return your body to that state. Notice the word here, or the acronym rather, EPOC. You'll see that term used interchangeably with oxygen debt. So it means the same thing. EPOC stands for excess post-exercise oxygen consumption. So it's the same as your debt. You see EPOC maybe used a bit more in magazines. And it usually just depends on the preference of the person that's writing. Right, let's take away those graphics. This slide is actually, I put it here not to so much talk about, but just you can pause the video. It's got, it's just a different graphical, and it's got some text in there that you might find handy to refer to. Everything I've said is sort of summarized in those two boxes. So it's a simplified version. Okay, so that's it. I've tried to keep it as short as I can, hopefully not too rushed for you, and hopefully not too slow as well. So I've tried to keep it under 20 minutes. It's going to be good. So a quick summary of what I've gone through is that there's a linear relationship between oxygen consumption and exercise intensity, simply because you require more oxygen when you increase the intensity of work. Okay, but we saw oxygen uptake increases slowly during initial stages when you're exercising. It takes a while for the aerobic energy systems to wind up. So what it gives, it leaves us with a bit of a lag between, or it leaves us with a bit of a, well, it's deficit, isn't it? So it leaves us with a deficit between what we actually want, what the body actually demands, versus what we can provide, and that lag is met, or the deficit is met, with anaerobic energy production. Okay, I realize you've probably read all these points by now, and that I'm just repeating them. Okay, and the last thing we went through is that because you have an oxygen deficit, you also have an oxygen debt, which is to repay that deficit, and it returns the body to homeostasis. Okay, you'll more on this in the lab. You're going to do a lab this week where you're going to analyze your own oxygen deficit and your own oxygen uptake kinetics, and you can do some work around economy, so I won't spoil that anymore, and Vincent can take you through that. Okay, hope you followed along this okay. I hope this recording turns out, because I don't want to have to re-record this again. Okay, more from me soon. There'll be one more lecture around VO2 max to go through.